Welcome to Calm and Clever. It's lovely to have you here tonight. Wherever you are right now, whatever corner of the world you've carried this little glow of a screen into, I'm glad you came. Maybe you're under a blanket, with the weight of the whole day finally lifting off your shoulders. Maybe there's a lamp still on somewhere across the room, soft and amber, the kind of light that isn't really for seeing by anymore, just for company. Maybe you're on a train or a couch or a bed that knows the shape of you. Wherever it is, settle in. You don't have to go anywhere. You don't have to do anything. For the next little while, the only task you have is to let your shoulders come down from around your ears and breathe and listen. So before we begin, I'd love to know, where in the world are you watching from tonight? What time is it in your corner of the night? If you feel like it, you can leave a little note in the comments, just a word or two, the name of your town or your country, or simply the hour glowing on your clock. I read them. It's one of the quiet pleasures of running a small channel like this, to imagine the whole soft scattering of you out there in the dark, some just lying down, some already half asleep, all of us pointed at the same handful of distant lights. And if you'd like more nights like this one, slow ones, gentle ones with something real and true at the center of them, a quiet like and a subscribe genuinely help this sleepy little channel keep going. Small creators like me really do rely on it more than you'd think. So thank you truly if you do. And to those of you already subscribed who come back night after night, thank you as well. You're the reason there's a tomorrow night. Now, I'll make you the same honest promise I always make. I'll try not to make this so interesting that it keeps you awake. But if it does, well, at least you'll have learned something lovely on the way. A fair trade, I think.
And here's the most important part. So let me say it plainly and then we'll never worry about it again. You do not have to stay awake for this. You don't have to follow every thread. You don't have to remember a single number or name. If you drift off in the middle, and I rather hope you do, the ideas will still be here, patient and unhurried, waiting for you whenever you wander back. There is no test at the end. There is nothing to grasp tightly.
We're going to move slowly, softly, one small wonder at a time, and you are allowed to let your attention go loose, like a hand opening in sleep. That's not failing. That's the whole point. Tonight we're going to spend our time with a single star, not the night sky in general, not a tour of the whole universe, just one star, one specific, particular named thing very far away that has been doing the same quiet act over and over since long before any of us were born. We're going to sit with it for a while. We're going to learn what it is and where it came from and the strange and gentle story of the people who first saw it.
100 small facts if we get to all of them, each one a little stone you can hold in your mind for a moment and then set down. There's no rush. We have all the time in the world and so does it. So, let's begin, shall we?
I want you to picture something for me, slowly, the way you'd picture a place you're falling asleep imagining. Picture a star, but not a great burning ball like our sun, wide enough to hold 1,000,000 Earths. No, picture instead a star that has been crushed down, squeezed in on itself, until the whole of it is only about 20 kilometers across. 20 kilometers. That's smaller than many cities. You could, in theory, drive from one side of it to the other in the time of a short morning commute, the kind where you barely finish your tea before you've arrived. A star you could cross before your coffee got cold. And this small thing, this little crushed bead of a star, is spinning, not slowly, not stately and grand the way you might imagine something so enormous and so far away ought to turn. It is spinning about 30 times every single second, 30 times, once around, completely around, every 33 thousandths of a second, faster than the blades of a fan in a warm room, faster than you can think the word around. A whole star, the crushed heart of something that was once unimaginably larger, turning over and over and over, 30 full turns in the space of a single heartbeat of yours. Sit with that for just a moment, because it's a strange and beautiful thing to hold in the mind right before sleep. A city-sized star, spinning 30 times a second, so far away that the light reaching you from it tonight has been traveling for thousands of years. And yet for all that violence of motion, all we ever perceive of it from here is a calm and steady ticking. Round and round, faithful as a clock. We'll come back to that. The idea of it as a clock, as one of the most patient and reliable things in all the sky. But first, let's simply ask the gentlest question there is. What is it? This star has a name, a real one, given to it by astronomers, and it's a name that sounds a little like a coordinate, because that's more or less what it is. It's called PSR B0531+21. Don't worry about holding on to that. Let it float past you like a number on a passing door. But that little cluster of letters at the front, PSR, is worth knowing because it tells you exactly what kind of thing this is. PSR simply stands for pulsating source of radio. A pulsating source. Something that pulses and that sends out a beat, a pulse, again and again with that lovely mechanical regularity. The rest of the name, those numbers, are just its address in the sky, its position written down so that anyone, anywhere, can point their telescope at the same patch of dark and find it waiting. But this star has a friendlier name too, a warmer one, the one most people use. We call it the Crab Pulsar, the Crab. We'll get to why it's called that, and it's a gentle little story involving an old drawing and a man with an enormous telescope in the Irish countryside. But, for now, just know it by that soft name, the Crab Pulsar, the pulsing heart of something called the Crab Nebula, which we'll also meet in time. So what is it really? What is a thing like this? It is a neutron star, and a neutron star is, in the simplest words I can find, the leftover core of a star that died. Not died gently, mind you, but we'll keep even that softly told. Once, a very long time ago, there was an enormous star out there, far larger and far heavier than our own sun. And like all stars, it lived its long life by burning, by holding itself up against its own crushing weight with the steady push of the fire at its center. But that fire can't last forever.
Eventually the fuel runs low. And when a star that large finally runs out of the thing that's been holding it up, its own gravity wins. The whole vast outer body of the star is flung away into space in a great quiet flowering of light. And what's left behind, at the very center, is the core. Crushed, compressed, squeezed down by gravity into that impossibly small, impossibly dense little sphere. That crushed core is the neutron star, that is, the Crab Pulsar.
The heart of something that ended still beating long after the rest of it has drifted away. And I called it dense. And I want to slow down here because the density of this thing is one of those facts that the mind can't quite hold. And yet it's worth turning over gently like a smooth stone before you sleep. Remember, this star is only about 20 kilometers across, city-sized, and yet packed into that tiny space is more mass, more sheer stuff than our entire sun. More than the sun. The sun, which could swallow 1 million Earths, which holds the whole of our solar system in its grip across billions of kilometers. All of that and more squeezed down into a sphere you could drive across before your coffee cooled. There's a way to picture just how dense that makes the material, and it's the kind of image that's almost soothing in its sheer impossibility. Imagine you could reach into this star and take out just a single sugar cube of its substance. just one little cube, the size of the one you might drop into your tea. That one small cube of neutron star material would weigh about as much as a mountain, on the order of 100 million tons. One sugar cube, 100 million tons. The matter inside this star is packed almost as tightly as the very nucleus at the center of an atom. And atoms, as you may know, are mostly empty space, with their nucleus a tiny dense speck in the middle of a great deal of nothing. A neutron star is, in a sense, what you'd get if you took all that emptiness out, if you crushed the empty space out of matter itself until there was nothing left but the dense heart of things, and that's what's turning out there. That's what's ticking 30 times a second in the dark. I find there's something strangely peaceful in that, lying here thinking of it. A thing so heavy, so impossibly concentrated, and yet from our distance so quiet, so faithful, so steady. All that crushing weight expressed to us as nothing more than a gentle, regular pulse, like a heartbeat heard through a wall. You don't feel the weight of the heart. You just hear the soft, sure rhythm of it, going on and on. Now, I told you this star has a story, and that the story reaches back a very long way, further than you might guess, because here is where it becomes not just a tale about physics, but a tale about people looking up. The story properly begins, for us, in the year 1054. Let that number settle for a moment. 1054, that's nearly 1,000 years ago. To put it gently in place, this is before the Norman conquest of England. This is a world without printing presses, without telescopes, without any of the instruments we'd later use to understand the sky. A world lit at night only by fire and the stars. And in that world, on a summer's night, the people who watched the heavens saw something appear that had not been there before. A new star, a light in a place where the night before there had been only the familiar dark. In China, this was taken very seriously indeed. The imperial court kept astronomers, careful, professional sky watchers, whose entire purpose was to record exactly this sort of thing, to note any change in the heavens and write it down. And these astronomers, working under the Song dynasty, did precisely what they were trained to do. They recorded it. We still have their records today, in documents with names like the Song Shi and the Song Huiyao, which are histories and collected records of that dynasty. Across the centuries, their careful note has survived, and it tells us what they saw and roughly when and where. They called it a guest star. Isn't that a lovely phrase? A guest star. In their words, a xing, a star that arrives like a visitor and stays for a while and then, in time, departs again. There's such gentleness in that idea that a new light in the sky isn't a portent of doom, isn't something to fear, but simply a guest, someone passing through, here for a season and then on its way. They didn't know what we know, that they were watching the death of a distant giant, the violent end of a star far larger than the sun. To them it was a guest, come quietly into the house of the sky, to be welcomed and recorded, and eventually seen off again into the dark. And where did this guest appear? In the constellation we now call Taurus, the bull, a patch of sky that rides high on winter nights in the northern half of the world, a quiet, ordinary region that most people pass over without a second glance. There, in July of the year 1054, the guest star arrived, and it was bright. This is one of the parts of the story where we should be a little careful, a little honest, because we're working from records written nearly 1,000 years ago, and then interpreted by historians much later. And honesty, I think, is part of what makes a story trustworthy enough to fall asleep to. But as those old records have been read and understood, it seems the new star was bright enough to be seen not just at night, but in broad daylight, in the daytime sky, for something like 23 days, over 3 weeks. This guest was visible even with the sun up, a point of light shining against the blue. Imagine that. Imagine going about your day, the ordinary business of a summer in the year 1054, and there, if you knew where to look, a new star hanging in the daylight. Steady, strange, unremarked in most of the world, but there. And then, slowly, as guests do, it began to leave. Over the following months, it dimmed, gradually, gently, fading from that daytime brilliance. The records suggest it remained visible at night for a good while longer, perhaps as long as 2 years, growing fainter and fainter, until at last it slipped below the threshold of sight and was gone. The guest had departed. The sky returned to its familiar self, and the new star, after its long, slow farewell, vanished from human view. But of course, it didn't really vanish. It only became too faint to see. Out there, in that same patch of Taurus, the thing that had caused the light was still present. The crushed core, the new little neutron star, beginning the very turning, the very ticking that it still performs tonight. The guest never truly left. It only quieted. And it has been there ever since, in the same place, doing the same patient thing, while 1,000 years of human nights came and went below. Now here is where I want to open a small, quiet thought for you. Not a worry, not a tension, just a soft loop to leave gently turning in the back of your mind as you drift. Because there's something about that year, 1054, that isn't quite what it seems. When those astronomers in China looked up in July of 1054 and saw a new star, they believed, naturally enough, that they were watching something happen. Right then, a star being born or appearing in that very moment. But that isn't really what was going on, because this star, this guest, is very, very far away, about 6,500 light years away. A light year, just so we're holding the same gentle idea, is simply the distance light travels in a year. And light is the fastest thing there is, fast enough to circle our whole Earth several times in a single second. In 1 year, light covers a distance almost too vast to picture, and this star is 6,500 of those years away, which means the light from its explosion, the light those Song dynasty astronomers saw shining in the daytime, had been traveling toward Earth for about 6,500 years before it ever reached their eyes. So when, exactly, did the star truly explode? Not in 1054. The flowering of light that the watchers saw in 1054 had simply finished its long, long journey across the dark in that year. The explosion itself, the actual event, the real moment the great star died and flung itself outward, had happened about 6,500 years earlier, which puts it somewhere around the year 5400 before the Common Era, 5,500 years before anyone in China wrote a single word about it. The star had already been dead, already been turning quietly into the thing we call the Crab Pulsar for all those millennia, while the news of its death came creeping across space toward us at the speed of light, until at last, in 1054, the news arrived. There's a calm and rather wonderful truth tucked inside this, and it's worth carrying with you as you settle deeper into the dark. In space, to look outward is to look into the past. Always. There's no way around it. Everything you see when you look up at the night sky is old light, light that left its source long ago and has only now arrived. The moon you see is a little over a second old, the sun 8 minutes, the nearest stars years. And this star, this Crab Pulsar, what we see of its birth is thousands of years old by the time it touches us. We are never quite seeing the universe as it is. We are seeing it as it was, layer upon layer of the past arriving all at once, each light carrying its own age. The watchers in 1054 thought they saw a new star being born. What they really saw was a very old letter finally delivered, a guest who had, in truth, set out on the journey to visit them 6,000 years before they thought to expect anyone at all. And that opens the gentlest of questions, one we'll come back to, so let it simply rest for now, without any need to answer it. If the people of 1054 were seeing light that was already ancient, then how much more so for us? When we point our telescopes at that same patch of Taurus tonight, the light we gather has been traveling for 6,500 years to find us. The pulse we record this very evening left the star while the world was an unimaginably different place. And the thing itself, the real star, the real turning core, what is it doing right now in this present moment that its light won't reach us in for thousands of years still? Is it still turning, still ticking, still there? We'll get to that, I promise you. We'll get all the way to that by the end. For now, just hold the soft shape of it. A guest star seen in daylight in 1054. A new light that was really very old light. A death that had already happened thousands of years before anyone saw it. And somewhere out there, in the same quiet corner of the sky, the crushed little heart of it all, turning and turning and turning. Let's stay with the people for a while longer, because the watchers of 1054 weren't only in China, though the Chinese records are the most careful and complete that we have. Across the world, in other lands, under other skies, there were other eyes turned upward that same summer. And the story of who saw the guest star and who wrote it down and who, strangely, seems not to have, is a gentle little mystery all its own. A quiet puzzle, the kind that's pleasant to turn over in a drowsy mind, with no urgency to solve it, no stakes at all beyond simple wonder at how differently people across the earth noticed, or failed to notice, the very same new light hanging in their very same sky. But that's a thread for a little further on. For now, let your breathing slow. Let the numbers drift away, or you don't need to keep them. Just keep the feeling of it. A small star far away, terribly heavy, turning 30 times a second, faithful as a clock. Seen once, long ago by people looking up. Still there. Still keeping its quiet rhythm in the dark, 6,500 years of distance between us and it. And yet, somehow in this moment, you and it sharing the same night. Rest now, just a little. We've only just begun, and there's so much more, all of it soft. The story of the cloud, the explosion left behind, the man who drew it and thought it looked like a crab, the young woman who first noticed the ticking and wondered, for a moment, if it might be a message. We'll wander to all of it, slowly, with no rush, and no test, and nowhere to be. For now, just listen to the rhythm of it, ticking away out there in the deep. Round and round and round. Let's go back then to the very beginning of it, not the beginning of the cloud or the drawing or the listening, but the beginning of the star itself. Or rather, the ending, because every neutron star is a kind of ending, a last quiet act after something enormous has finished burning. The thing that became the Crab Pulsar was once a giant, a true giant, a star far larger and far heavier than our own sun, perhaps 8 times its mass, perhaps as much as 20. Hold that for a moment, gently, without straining. Our sun is already a thing so large that more than 1 million Earths could fit inside it. And the star that died to make the crab was many times heavier still. A vast blazing thing holding itself open against its own enormous weight by the heat and light pouring out of its core. And that's really all a star ever is, in the simplest telling. A long, patient argument between two things. Gravity, pulling everything inward, always relentlessly, trying to crush the star down into a single point. And the fire at the center, pushing outward, holding the whole thing up. For millions of years, those two forces stay almost perfectly balanced. The star burns, the fire holds, gravity waits, a long, steady truce. But the fire needs fuel, and one day, and for a star like this, one day comes after only a few million years, which is a short life as stars go, and the fuel begins to run out. The fire at the heart starts to falter, and the moment it does, the truce breaks. Gravity, which has been waiting all along, patient and tireless, finally wins. What happens next happens fast, faster than you can really picture, so don't try too hard. The core of that giant star, a core already larger than our entire sun, collapses inward, not over years, not over hours. In less than a single second, a structure wider than the sun falling in on itself in the time it takes to say one short word. And it falls until it simply can't fall any further. The matter is squeezed so hard, so suddenly, that the very atoms inside it give way. Now, you don't need to follow the physics of that, not tonight. Just hold the picture. An almost impossibly heavy thing crushed down and down, until what's left is a sphere only about 20 kilometers across, city-sized, the width of a quiet town holding more mass than the sun. That's the star, that's the Crab Pulsar, born in a single second, out of the death of something far, far larger. And when the core fell in like that, all that infalling weight rebounded, and the outer layers of the old giant, everything that wasn't the core, were flung outward into space in a single, soundless burst of light. That's the explosion. That's the supernova. That's the light that crossed 6,500 years of darkness and arrived at last in a summer sky in 1054, bright enough to see in daylight, while people far below looked up and quietly wondered what it was. So when those Song dynasty astronomers wrote down their xing, their guest star, arrived in the constellation we now call Taurus, lingering for 23 days in the daytime, and then fading slowly over 2 long years, they were watching the outer skin of a dead giant blow away into the dark. They didn't know that, of course. They couldn't have. They simply saw a new light where there had been none, recorded it carefully, faithfully, as was their custom, and then watched it go. Song Shi, Song Huiyao. Names of records kept by people whose own names we've mostly lost, doing the patient work of looking up and writing down. Centuries of careful watching, all so that you, tonight, could know almost exactly when this star was born. And here's the thing to rest on, the gentle weight at the center of all of it. They thought they were watching something arrive, a guest, something new. But the explosion they saw hadn't just happened. It had happened long before, and around 5,400 years before the birth of Christ, when the light first left the dying star. The star sits about 6,500 light years away.
And a light year, that comforting old word, is simply the distance light travels in a single year, racing along at the fastest speed anything can go, 6,500 of those. So the light had to travel for 6,500 years just to reach the eyes of those astronomers in 1054.
Which means the explosion they recorded as new was, in truth, ancient even then. Older than the pyramids, older than writing itself in most of the world. By the time anyone on Earth saw that star, it had already been spinning quietly in its nebula for thousands of years, unwatched, unrecorded, simply turning in the dark while empires we've forgotten rose and fell beneath it. That's the soft, strange truth of looking up at anything far away. You are never seeing it as it is. You are only ever seeing it as it was. The further out you look, the further back in time you're looking. The starlight that reaches your window tonight is old light, patient light, light that began its journey long before you, sometimes long before anyone. To look outward into the deep is simply to look into the past. Gently, with no way to hurry it and no need to. And what came back to those astronomers after that long, long crossing, it is what they finally saw, was the death of a giant. But cradled inside that death, hidden at the very heart of the blast, was the thing that survived, the crushed core, the neutron star, 20 kilometers wide, heavier than the sun, and already beginning to do the one thing it would never stop doing. Spinning, because when a great, slow-turning star collapses down to so small a size, it spins faster, far faster. You may have seen this without ever thinking of stars at all. A figure skater turning on the ice, arms held wide, spinning slowly, and then they pull their arms in tight against their body. And without any push, without any effort, they spin faster, faster and faster, simply because they've gathered themselves in. That's all the Crab Pulsar did, on a scale almost impossible to hold in the mind. A star wider than the sun, gathering itself into a city-sized ball and spinning up and up until it was turning not once a year, not once an hour, but dozens of times every single second. 30 times a second, once every 33 thousandths of a second, faster than the blades of a fan in a warm room. A whole star, a thing heavier than the sun, turning over completely 30 times in the time it takes you to draw one slow breath. And it has been doing exactly that faithfully without rest, every moment since before those astronomers wrote it down, round and round, in the dark, 6,500 years away. And the density of it. Let this one settle softly, because it's the kind of fact that sounds impossible and somehow soothing both at once. A piece of this star, no bigger than a sugar cube, the little white cube you might drop into evening tea, would weigh about 100 million tons. A small mountain folded into a thing you could hold between two fingers. The matter inside it is packed almost as tightly as the nucleus at the very center of a single atom, as though someone had taken all the empty space out of ordinary matter, all the gentle, roomy gaps that make a chair, and a hand, and simply pressed it away. What's left is the Crab Pulsar, heavier than you can picture, smaller than a city, turning in the night. You don't have to understand how that's possible. The physicists who study it spend whole careers on the question, and they'll tell you, with the lovely honesty of people who really know, that there is still a great deal they don't fully understand about what goes on inside it. So you're in good company, lying here, not understanding, simply marveling. That's allowed. That's the whole invitation tonight, not to grasp it. Just to let it be strange and beautiful and far away, and to let that strangeness rock you very slowly towards sleep. So there it is, the shape of the thing, the heart of the whole story. A massive star dying in a single second. A core crushed down to a heavy little sphere. A light flung across 6,500 years of darkness to arrive in a summer sky and be written down by careful hands. And at the center of it all, hidden inside the fading cloud, a city-sized star, PSR B0531+21, the pulsating source of radio we call the Crab Pulsar, spinning 30 times a second, keeping a rhythm older than history, faithful as any clock. There's so much more to wander through, and we will, slowly. The cloud the explosion left behind, still glowing, still expanding even now. The way this little star ticks and slows, and every so often gives a tiny, gentle hiccup. The way we can see it blink, not just in radio waves, but in ordinary light, and listen to its pulse as a soft and steady sound, almost a heartbeat. All of that is ahead, all of it soft, none of it in any hurry. But for now, just hold the simple picture. A small, heavy star turning quietly in the dark. Seen once, long ago, by people who looked up. Still spinning tonight. Round and round and round. And we were not the only ones who looked up. That is one of the quiet, wonderful things about the 1054 guest star. It was not seen by one culture, written down by one careful hand, and then forgotten. It was seen by many. Across continents that had no contact with each other, across languages that shared no common root, people went outside, looked at the same patch of sky, and noticed the same new light. They found different words for it. They kept their records in different ways. But they were all watching the same thing, the same expanding sphere of fire, the same light that had been traveling for 65 centuries, finally arriving once at this small blue world. The most detailed records we have come from China. The astronomers of the Song dynasty were precise, methodical people. Their job was partly to interpret the skies for the court, to watch for signs, to record changes, and to keep careful accounts of anything unusual. A new star appearing where no star had been before was exactly the kind of thing they were trained to notice and document. The records preserved in the Song Shi, the official history of the Song dynasty, and in the Song Huiyao, describe what they called a xing, a guest star. The term is gentle, isn't it? Not an alarm, not a portent of doom, just a visitor, something that arrived, stayed a while, and then departed, as guests do. The word has a kind of hospitality to it, a quiet welcome, extended even to something so strange. They recorded it appearing in what we now call the constellation Taurus the Bull in the summer of 1054, specifically in July of that year. And they kept watching. They noted that it was bright, remarkably bright, brighter than any star nearby, and, according to those accounts, bright enough to be seen even in daylight, even when the sun itself was in the sky. They say it held that extraordinary daytime visibility for around 23 days, 23 mornings and afternoons when a careful observer, knowing where to look, could find a star in the broad blue daylight. After that, it dimmed, gradually, slowly, but it didn't disappear quickly. It lingered in the night sky for roughly 2 years, slowly fading before finally slipping below the threshold of what the eye could detect. And then it was gone. The guest had departed. We should hold the daylight figure gently with appropriate care. The historical records are real, and they are our best evidence. But historians of astronomy are honest about the fact that records from this distance in time are interpreted, transcribed, sometimes copied from copies, sometimes summarized by later writers. The 23 days of daytime visibility is drawn from those accounts, and astronomers working backward from what we know about such explosions think it's plausible a supernova of that brightness at that distance could indeed have rivaled the moon for a short while. But could have, and definitely did, are different, and the science of this is careful to keep them separate. We take these numbers as the best record we have, honored but not overinflated. And then, across the world to the east, another hand was writing. Japan in 1054 was in the Heian period, a time of elegant court culture and careful literary record-keeping. The astronomer Fujiwara no Sadaye, also known as Taker, is associated with a later transcription of astronomical diaries from that era. The Japanese records are less detailed than the Chinese ones, but they corroborate the core observation, a bright new star appearing in the appropriate part of the sky, noted by watchers who knew the night sky well. Different language, different tradition, different side of a vast ocean of land, and yet the same entry in the log. Something is here that was not here before. And then further still, in a different direction entirely, in the world of medieval Islamic scholarship. An Arabic writer named Ibn Butlan, a physician and intellectual who traveled widely across the Near East, recorded what appears to be the same phenomenon around the same period. His account survives in a form that suggests he too noticed or knew of a remarkable new object in the sky. Ibn Butlan was not primarily an astronomer. He was a doctor, a scholar, a man who wrote about food and medicine and philosophy, but he was the kind of curious, careful observer who noted what the world around him was doing. His mention of the star adds to the chorus. A different voice, a different language, the same astonishing light. There is something quietly moving about this, if you let yourself feel it. These people did not know each other. They had no radio, no telegraphs, no shared system of scholarly communication that would have let them compare notes in anything close to real time. They simply saw the same sky, and independently, separately, they thought it was worth writing down. The light from a star that had exploded 5,500 years before their time reached their eyes during their lifetimes, and they said, "This is unusual. This is worth recording." And so they did. And so, 1,000 years later, we have their accounts, and we have the glowing cloud still expanding in that same patch of sky, and we can hold all of it together and say, yes, that was the same event. You were right to look. You were right to write it down. And then there is a third proposed witness, one that requires a little more care. In the American Southwest, we do in places where the ancestral peoples of the region made their records not in written text, but in images on stone, there are pictographs and rock art images that some scholars have suggested might also record the 1054 event. There is a recurring image found in several locations of a crescent and a bright dot nearby. A crescent, of course, being the moon. A bright dot nearby being perhaps a bright star. If the position of the moon at the time of the 1054 supernova is calculated, and it can be, the moon was indeed a crescent, and it was close in the sky to where the new star appeared. The geometry works out in a way that is tantalizing. It is possible, genuinely possible, Barsham, that what is painted on some of those canyon walls is a memory of that same morning in 1054, a bright new visitor near the crescent moon, painted by someone who was moved enough by what they saw to make it permanent. But this is proposed, not proven. Archaeoastronomers debate it. The images are real, the proposed interpretation is reasonable, but rock art is hard to date precisely, and the same crescent and star image has other possible explanations in the traditions of those who made it. And this is one of those places where the honest thing to say is we don't know for certain. It may be, it might be. There is a version of that morning in 1054 where a child in a canyon in what is now the American Southwest looked up at a crescent moon with a new, bright star sitting just beside it, and later someone painted it on a wall, and that painting is still there. That story might be true. We simply cannot confirm it with the certainty we'd like, and so we keep it at arm's length. A soft, maybe, a beautiful possibility. And then there is the silence. You might expect that a star so bright it could be seen in daylight, a star that lasted in the sky for 2 years, would be written about everywhere. That monks in their scriptoria, scholars at their desks, court chroniclers at their tables across Europe would all have looked up, been astonished, and made a note. And yet the European record is, to put it gently, thin, almost absent. There are a few possible references here and there, debated by historians, but nothing that clearly, unmistakably records what the Chinese and Japanese astronomers described so matter-of-factly. Why the silence? No one knows for certain. Various explanations have been offered. The nature of European astronomy at the time focused more on interpretation than raw observation. the possibility that the star was better placed for observers in China and Japan at the time of year it appeared. The filtering of records through monastic and scholarly traditions that may not have preserved every observation. But none of these fully explains it. It remains one of the quiet, genuine puzzles of this story, a small gap in the historical record that historians still find interesting. The guest star visited Europe too. We just don't seem to have kept the guestbook entry. There's something fitting about the mystery, actually. A story that is mostly confirmed, beautifully corroborated across cultures, and then has this one unexplained gap right in the middle of it. That's what a real story looks like. Not everything sewn up neatly. One thread left loose. So the sky of July 1054 was lit by something new, and people noticed, and after about 2 years, the light that could be seen with the naked eye faded and was gone. The guest had departed, and for centuries, the sky in that part of Taurus looked normal, or nearly so, to anyone watching with just their eyes. But something was still there. Something growing, spreading, slowly expanding outward at its tremendous speed. A cloud of debris, a thinning but still glowing shell of gas and magnetic field and swept-up material, gradually cooling, gradually dimming, but dimming on a time scale of centuries, not years. The wreckage of the explosion drifted outward, steadily, quietly. It was a comet hunter who first gave it a name, in a way. Charles Messier was a French astronomer in the 18th century, and he had a very specific professional obsession. He wanted to find comets. New comets, unexpected comets, comets that no one had catalogued before. In the 1750s and 1760s, he dedicated himself to this pursuit, scanning the sky methodically, looking for fuzzy, diffuse blobs of light that moved against the background of stars. That movement was the key. A comet drifts slowly across the sky over days and weeks while stars stay still. So Messier would find a fuzzy blob, watch it for a while, and then decide whether it was a comet worth tracking or simply a nuisance. A fixed, non-moving cloud of gas that looked comet-like but stubbornly refused to go anywhere. The first object on his list of nuisances, the things he carefully catalogued specifically so other comet hunters wouldn't waste their time on them, was a softly glowing oval in Taurus. Messier number 1, M1. First on the list, not because it was the most important, but because it was the most comet-like, the most likely to fool you into thinking you'd found something that was in fact going nowhere. He documented it so it could be dismissed. It became one of the most studied objects in the entire sky. He would presumably find that somewhat ironic. We know now, of course, that M1 is the Crab Nebula, the expanding wreckage of the 1054 explosion. Messier didn't know that. He couldn't have known it. The connection between historical guest stars and these diffuse, cloudy objects was not understood in his time. He saw a fuzzy patch. He noted it down. He moved on, looking for comets. The name Crab Nebula itself came later, in 1842, from an Irish nobleman and amateur astronomer named William Parsons, the 3rd Earl of Ross, who is known to history simply as Lord Ross. He had built on his family estate at Birr Castle in County Offaly in Ireland the largest telescope in the world, a vast reflecting instrument with a 6-foot mirror mounted in enormous stone walls, a structure so remarkable it was known by everyone in the field as the Leviathan of Parsons Town, Parsons Town being the old name for the town of Birr. With the Leviathan, Lord Ross could see details in distant nebulae that had been invisible before. When he turned it on Messier's first object, he was able to make out something of its structure. Delicate filaments, a complex inner shape. He sketched what he saw, and his 1844 sketch resembled, to him, a crab. The name stuck, as the good informal names always do, immediately and permanently, even though his later and better sketches, made as his technique and instruments improved, actually looked considerably less crab-like. By then, the Crab Nebula was already the Crab Nebula, and so it has remained. Lord Ross's work was itself a kind of wonder, a private citizen in rural Ireland building the world's largest telescope in his own yard, turning it toward the sky and drawing what he found there with careful pencil lines. The Leviathan was a remarkable piece of engineering for its time, and it gave astronomy some of its first real glimpses into the structure of what we call nebulae. The crab in particular benefited from his attention. It was Lord Ross's crab, and Charles Messier's nuisance, and the song Dynasty astronomer's guest. All the same cloud of slowly cooling gas, seen at different times through different eyes. This expanding cloud, the Crab Nebula, is not small. It stretches across roughly 11 light-years from one side to the other. Light itself, the fastest thing in the universe, takes 11 full years to cross it. It sits about 6,500 light-years from Earth, and at that distance its apparent size in the sky is modest. You need a telescope to see it, and under bright city lights you can't see it at all. But in terms of actual physical scale, it is enormous. It is a structure many times wider than the distance between our Sun and its nearest stellar neighbors. And it is still growing. Even now, the gas and filaments of the crab are pushing outward, expanding into the thin gas of interstellar space at roughly 1,500 kilometers per second. 1,500 kilometers every second. That is a speed so large it almost resists visualization. But the nebula is also so large that even at this speed, the expansion happens slowly on the scale of a human life. You'd need to compare photographs taken decades apart to notice the change, and astronomers have done exactly that. Images taken in the early 20th century compared to images taken decades later show the cloud measurably larger. Within the span of the history of modern astronomy, we have watched this cloud grow. We have been here long enough to see the wreckage spread. Working backward from its current size and rate of expansion, astronomers can calculate when the expansion must have started, and it comes out, reassuringly, close to the year 1054. That is one of the beautiful confirmations at the heart of this story. The math of the expanding shell and the written records of the Chinese astronomers point at the same event, independently, and they agree. The guest star of 1054 made the Crab Nebula. The light that was written down in the song She and the Crab Nebula in front of our telescopes today are the same thing seen at different moments in its long, slow unfolding. So you have the cloud, this great, slowly spreading wreckage. And at its heart, hidden and small and extraordinarily dense, is the object we're spending tonight with. To understand how we found it and what it is, we need to follow a thread that begins not in 1054, but in 1967 in a field in England, with a young woman and a pile of chart recorder paper. Jocelyn Bell Burnell was a graduate student at the University of Cambridge, working under Anthony Hewish. Her project was to build and operate a radio telescope, a large array of antennas spread across a field, designed to study how radio signals from distant sources were twinkling, blurred and flickered by clouds of charged particles in interplanetary space in a way roughly analogous to how stars twinkle in the optical sky when seen through the atmosphere. It was careful, systematic work, and it produced a lot of data. Hundreds of feet of chart recorder paper scrolling through the night, recording the fluctuating signals from the radio sky. Bell Burnell was diligent. She read the charts. She knew what the signals were supposed to look like. And she noticed something strange. She'd a little patch of signal that didn't look quite right. It appeared at the same point in the sky, at the same time each day, too regularly and too compactly to be the twinkling she was looking for. She described it later as a bit of scruff, a small, anomalous squiggle on the chart paper that she kept her eye on rather than dismissing. The instinct of a careful scientist, this doesn't fit, so I'm not going to ignore it. When the team examined the anomaly more closely, with a faster chart recorder that could capture more detail, they found something that honestly, genuinely surprised them. The signal was pulsing, not blurring or twinkling. Pulsing, coming in short, discrete bursts, repeating with extraordinary regularity. Each pulse separated from the next by exactly the same interval. They measured the period, one pulse every 1.3373 seconds, with a precision that made most man-made clocks look approximate. Whatever was out there was keeping time in a way that put ordinary clockwork to shame. The regularity was, and this is not an exaggeration, so extreme that one of the things the team briefly considered was whether this could be artificial. A regular, repeating signal from a fixed point in the sky, it had the quality of a transmission. A beacon, something designed to be counted. They called the signal, with a tone that was partly serious and partly whimsical, LGM1, Little Green Men 1. It was a joke, but it was a joke that acknowledged the unsettling thought. What if it's not natural? It quickly became clear that it was natural. When Belle Burnell found more pulsing sources in other parts of the sky, and she did within weeks, the idea that these were signals from extraterrestrial beings became very hard to sustain. The sources were scattered around the sky, each pulsing at its own distinct rate, some fast, some slower. No plausible sender could be in that many places at once. What they had found was a new kind of astronomical object, something that had never been observed before, something pulsing with the regularity of a clock, because it essentially was a clock, though not of any design but the universe's own. These were pulsars. The name was coined by a journalist and adopted by the scientific community almost immediately. It describes what these things do. They pulse. Short, regular, precise pulses of radio waves from a point-like source. The question was, what are they? Several ideas were put forward, each with its merits. Perhaps they were pulsating stars, contracting and expanding rhythmically. Perhaps they were something in orbit, a pair of objects circling each other, one eclipsing the other with each rotation. And then there was the suggestion of Thomas Gold made in 1968, which turned out to be correct. That what they had found were rotating neutron stars, a spinning star with its radio beams sweeping through space, giving a pulse with each rotation, just as a lighthouse gives a flash with each turn of its light. The rotating neutron star model made a specific prediction that could be tested. If pulsars were spinning objects, slowing down gradually as they gave up energy, then their pulse periods should be getting slightly longer over time. The pulses should arrive a little more slowly as the years went on. This was measurable, and when the measurements were made, that is exactly what was found. But the most convincing confirmation came from the Crab. When astronomers searched the Crab Nebula, it's already known to be a supernova remnant, the wreckage of an explosion, they found a pulsar right at its heart. The Crab Pulsar, identified in 1968, a pulsing source of radio waves sitting at the center of the cloud left by the 1054 explosion at the precise location where a neutron star should be. And its pulse period was about 33 milliseconds, much faster than the original discovery, spinning roughly 30 times a second. And it was slowing, measurably, steadily slowing. This was the confirmation that sealed the model. Here was an object whose birth date was known, 1054 give or take, verified by independent historical and astronomical evidence. Here was an object sitting exactly where the neutron star model predicted a remnant core should be. And here was an object whose behavior, its rotation, its slowdown, the energy it was pouring into the surrounding nebula, all matched what a young, energetic, spinning neutron star should look like. Gold's prediction was vindicated. The mystery of pulsars was, at its core, the mystery of spinning neutron stars, and the Crab Pulsar was the key piece of evidence that locked it in. The discovery of pulsars was recognized with the Nobel Prize in Physics in 1974, awarded to Anthony Hewish. Jocelyn Bell Burnell, who found the signal, read the charts, noticed the scruff and refused to dismiss it, was not included in that prize. It is a historical footnote that many people in astronomy find uncomfortable, and it is the kind of thing that is simply worth knowing, said plainly, without dwelling on it in a way that turns this peaceful story into something else. She did the work. The work was recognized. She was not. She has spoken about it with more grace than most people would manage. We note it and move on, carrying it. But let's return to what the Crab Pulsar confirmed and what it showed the world. The fact that pulsars are rotating neutron stars had been proposed, but the Crab made it concrete, observable, undeniable. Because the Crab's age was known, it anchored everything. It told astronomers this is what a neutron star looks like when it's young, less than 1,000 years old. It's spinning fast, very fast, and it's slowing down, and the energy it releases as it slows is what makes the nebula around it glow. That connection between the spinning star and the luminous cloud was not obvious before. It became one of the central insights of modern astrophysics. But the Crab Pulsar's discovery also confirmed something that two scientists in the 1930s had proposed in a paper that was, at the time, considered somewhat audacious. Walter Baade and Fritz Zwicky, working in the United States, had published a remarkable paper in 1934. In it, they suggested that when a massive star runs out of fuel and its core collapses, the result could be an extraordinarily dense remnant, a star made almost entirely of neutrons, the subatomic particles with no electrical charge that make up part of the nucleus of every atom. They called this a neutron star. The idea was considered bold, in part because the neutron itself had only just been discovered in 1932, barely 2 years before their paper. Baade and Zwicky took the newly discovered particle and proposed that under the right circumstances, you could have an entire star built from it, a dense, collapsed, unimaginably compact remnant. And they suggested this was what supernovae, the explosive deaths of massive stars, produced. It took decades for instruments to be built that could detect these objects. But when they were, and when Jocelyn Bell Burnell's chart recorder picked up that bit of scruff in a field in England in 1967, the prediction of Baade and Zwicky was waiting to be recognized in the data. The 1934 paper and the 1967 discovery, held together, are a quiet triumph of the scientific process. A bold idea, patiently vindicated on a timescale that spans most of a human lifetime. There is something deeply calming about that. The universe keeping its promises on its own schedule. And so the Crab Pulsar became, very quickly after its discovery, one of the most intensely studied objects in all of astronomy. It was a young pulsar of known age in a well-studied nebula, visible across a remarkable sweep of the electromagnetic spectrum, meaning that every kind of telescope, from radio dishes to optical instruments to X-ray observatories to gamma-ray detectors, had something to say about it, including the fact that its pulse can be seen in visible light. This is genuinely rare. Most pulsars pulse only in radio waves. They are invisible to an ordinary optical telescope, known only by their radio emissions. The Crab Pulsar, because it is young and energetic and pouring an enormous amount of energy outward, pulses in optical wavelengths too. It was first detected blinking in visible light in 1969. If you could somehow stand next to a very fast camera pointed at that spot in the sky, you would see it. 30 brief flashes of visible light every second, too fast for the human eye, which blurs them all together into what appears to be a dim, steady point. But instruments with sharp enough time resolution can resolve each individual flash. The star quite literally blinks in ordinary light 30 times a second, a lighthouse visible not just to our radio ears, but to our optical eyes, and it pulses in radio, in infrared, in ultraviolet, in X-rays, in gamma rays, the most energetic form of light. Almost the entire electromagnetic spectrum, from the long, lazy wavelengths of radio to the sharp, high-frequency bursts of gamma radiation, carries the Crab signal. It is one of the most broadly visible objects we know. A single, small, dead star shouting in nearly every language the cosmos has available. The pulsar's two beams, the lighthouse beams, that produce each pulse as they sweep past Earth, are not aligned with the axis around which the star spins. This is the key to the lighthouse model. If the beams came out along the spin axis, straight out the poles, north and south, and if we happened to be sitting exactly on that axis, we might see a continuous glow rather than a pulse. But the beams are tilted relative to the spin, pointing out at an angle. And so with each rotation, each 33 millisecond turn, the beam sweeps through space in a wide arc like a lighthouse lantern. And for a brief moment in each sweep, it points toward us, and we see a pulse. Then it sweeps away, and we see nothing from that beam until the next rotation brings it back around. There are actually two pulses visible from the Crab in each full rotation. A main pulse, bright and sharp, and then a secondary, smaller pulse called the interpulse, which comes roughly halfway between main pulses. The main pulse and the interpulse are thought to come from the two opposite beams of the star, each one sweeping past us in turn during a single rotation. So in effect, every 33 milliseconds you get two little bursts of light, a heartbeat with a softer second beat, like the lub-dub of a real heart. The main pulse and the interpulse together are the Crab Pulsar's signature. Its rhythm, its voice, if you want to give it a gentle metaphor. And that voice has been speaking beam sweeping across the galaxy every moment since the moment the star was born in the collapse of 1054. Since before there was a Crab Nebula to show, since before there was a pulse to receive, in all the centuries before anyone had built an instrument sensitive enough to hear it. That beam swept past Earth in 1067, in 1200, in 1453, in 1776, in 1900, every 33 milliseconds, year after year, century after century, the lighthouse turned. Nobody was listening. Nobody had the right kind of ear. But the turning didn't stop because physics doesn't care whether anyone is listening. It just keeps going. And then, in 1967, in a field in England, a young woman with a careful eye and a piece of chart recorder paper was finally in the right place with the right instrument to notice. There is a kind of tenderness in that too, if you let it land. All that turning, all those centuries of silent pulses waiting. Not waiting in any intentional sense, nothing so human as that. Simply persisting, as physics persists, until the technology and the attention finally arrived to receive what had been broadcast all along. The light we see from the Crab Nebula tonight, incidentally, is not light from the star itself. Not light the star is producing now. The light takes about 6,500 years to reach us. So what we see tonight left the pulsar during the Copper Age, more or less, when human beings were beginning to work metal and the oldest cities were still new. The pulse arriving at your nearest radio telescope at this moment left the Crab Pulsar before the pyramids of Giza were built. It has been traveling through interstellar space, crossing distances beyond easy imagination, since before most of what we think of as civilization existed, and now it arrives, still regular, still precisely timed, to be detected by instruments on a small planet whose inhabitants are, among other things, lying in bed, listening to someone talk about it. That is a thought worth floating in gently, without hurry. The cloud that holds the pulsar, the Crab Nebula, Messier 1, the first entry on a comet hunter's list, of distractions, Lord Ross's crab, the xing debris, is still spreading. 1,500 kilometers per second in every direction, the ancient gas of the star's outer layers moves outward into space. 11 light-years across and growing. The blue inner glow, the red outer filaments, the soft oval shape visible in a good amateur telescope from a dark enough field, all of it slowly, imperceptibly, to a human eye, watching for a human lifetime, but measurably to a camera comparing photographs taken 100 years apart, growing larger. And at the center of all that expansion, the heartbeat persists, round and round, 30 times a second, a pulse across radio waves, a pulse in visible light, a pulse in X-rays, a pulse in gamma rays. The lighthouse turning, as it has turned, every 33 milliseconds for 1,000 years of counted time. We have come a long way tonight already, and there is more still to discover. The strange interior of the star itself, the way its slow winding down lights the whole nebula, the quirks and hiccups of its rhythm, the ways it has served as an instrument in our hands, a clock and a calibration and a probe of the universe around it. The sound it makes, converted into something your ears could hear, that waits quietly ahead. But let's rest here, just for a moment, in what we've found. In the human chorus of July 1054, the Song dynasty astronomers with their careful records, the Japanese witnesses, the Arabic physician noting a strange new light, the possible painters of a canyon wall, in the century-long slow dawn of understanding that connected that ancient record to a glowing cloud in Taurus, in the comet hunter who catalogued it as a nuisance and gave it a number, in the Irish nobleman with his enormous telescope in a field making sketches in the lamplight, in the young graduate student in England with her chart recorder paper and her refusal to dismiss what didn't fit. All of them, in their different ways, following the same light. All of them, in their different ways, doing what humans do when something in the sky catches their eye. They look more carefully, they reach for something to write with, they try to understand. The Crab Pulsar has been at the center of that long human looking, patiently turning. Indifferent to our attention, but illuminated by it generation after generation, telescope after telescope, theory after theory, each one bringing us a little closer to understanding what exactly is sitting dense and blazing and precise at the heart of that soft, expanding cloud. And tonight, it's still there, still turning. So let us talk about the slowdown. It is, in its own quiet way, one of the most remarkable measurements in all of astronomy. The Crab Pulsar is slowing down, not dramatically, not in a way you could ever feel or see with your own eyes, but measurably, steadily, day after day, in a way that our instruments have been recording for decades now. And the number we have arrived at, the precise figure for how much it slows each day, is so small it almost defies description, and yet so exact it almost defies belief. Each day, the Crab Pulsar's spin period grows longer by about 38 nanoseconds. Let that sit for a moment. 38 nanoseconds. A nanosecond is 1/billionth of a second. If you were to blink, a normal, unhurried blink, that action would take somewhere around 150 million nanoseconds. The Crab Pulsar slows in a full 24 hours by about 38 of those billion slices of a second. Not 38 of your blinks worth. 38 of those impossibly thin slivers, the kind of time that has no analog in ordinary life. And yet we know it, we have measured it, telescope after telescope, year after year, timing the arrival of each pulse with clocks precise enough to catch that tiny daily drift. The measurement exists, the number is real, and the fact that it is real, that something so small is knowable at all across a distance of 6,500 light-years is, if you let it, a kind of gentle miracle. Fact 29 on our long, slow journey tonight. Fact 30. And here is what that tiny slowdown means if you follow it outward. The Crab Pulsar is a spinning object, and like all spinning objects, it carries energy in its rotation. When it slows even by 38 nanoseconds a day, it is shedding that rotational energy. Physics is clear on where that energy goes. It flows outward into the space around the star. And when you sit down and calculate how much energy is implied by even that tiny daily deceleration applied to an object that weighs more than the Sun and spins 30 times a second, the answer is staggering. The pulsar is losing energy at a rate equivalent to roughly 100,000 times the total power output of our Sun. 100,000 suns worth of power every single second bleeding away from one small turning star. And where does it all go? That is the next piece of the picture, and it is a lovely one. Fact 31. All of that outflowing energy does not simply vanish into the dark, it streams away from the pulsar in what astronomers call the pulsar wind. A fierce, continuous outpouring of high-energy particles, electrons and positrons, hurled outward by the churning magnetic field of the star. The pulsar wind fills the space around the Crab Pulsar and pushes outward against the expanding shell of the supernova remnant, and in doing so, it keeps the entire Crab Nebula alive. The Crab Nebula is not a passive object. It is not simply a cloud of gas coasting away from an old explosion, gradually cooling and dimming as old supernova remnants normally do. It is an active, powered system. The pulsar sits at its heart like a small, blazing engine, and the wind that pours off it is what keeps the nebula glowing. Without the pulsar, the Crab Nebula would simply fade over thousands of years, its particles losing energy and its glow dimming, until it became just another invisible wisp of cold gas in the constellation Taurus. With the pulsar, it burns. This is why astronomers call it a pulsar wind nebula. The Crab Nebula is the textbook example of this class of object, the best studied, the closest, the most clearly understood. The pulsar gives energy, the wind carries it, the nebula spends it as light. Fact 32. The mechanism by which the nebula shines is called synchrotron radiation. It is a name that comes from a type of particle accelerator, because the process is the same. When charged particles are forced to travel in curves through a magnetic field, they emit light. In a particle accelerator, engineers design the curves deliberately. In the Crab Nebula, the magnetic field threading through the whole system curves the paths of the wind particles automatically, and they glow. The light they produce has a soft, bluish quality in photographs. It is the inner, smooth, textured glow you see when you look at the crab, that hazy, faintly luminous cloud that fills the interior. That is synchrotron radiation. That is the Crab Nebula's breath powered by the pulsar's spin. Fact 33. And then there are the filaments, around the edges of that inner glow, wrapping the whole system like a delicate net or a basket, are the red and orange threads of glowing gas that give the crab its distinctly structured appearance. These filaments are the original outer layers of the star that exploded, the actual material that once formed the shell of a massive star, now scattered into a lacy web across 11 light-years of space. They glow largely in hydrogen, lit up by the energy streaming outward from the pulsar at the center. In long exposure photographs, they are gorgeous, crimson threads against the blue-white inner cloud, like an ember held together by the finest possible mesh. Together, the soft inner glow and the outer web of filaments make the Crab Nebula one of the most beautiful objects in the sky. Astronomers often say so, not as a judgment of taste, but almost as a matter of fact. It is a quiet, multi-layered beauty, the kind that rewards patience and magnification, that reveals more the longer you look. Fact 34. So, the pulsar slows. The energy flows outward as a wind. The wind inflates and powers the nebula. The nebula glows in hydrogen at its edges and synchrotron radiation at its heart. One system, one object, one continuous chain of cause and effect, running from a city-sized spinning star to a cloud 11 light-years across. It is, in its own gentle way, a complete and elegant story. But how did we come to understand any of this? The pulsar was not discovered until the late 1960s. The nebula had been known for 2 centuries by then. The physics, the model, the picture we now take for granted, all of that had to be assembled piece by piece by people working with imperfect instruments and incomplete theories, following clues that didn't always fit. And the story begins even before the pulsar was found. It begins with a prediction made in 1934, more than 3 decades before anyone detected a pulsar signal. Fact 35. In 1934, 2 astronomers named Walter Baade and Fritz Zwicky published a remarkable paper. They were thinking about supernovae, the great stellar explosions that occasionally appeared in distant galaxies and briefly outshone everything around them. What, they asked, happened to a star when it exploded that violently? Where did the energy come from and what was left behind? Their answer was extraordinary for its time. They proposed that a supernova could be produced when a massive star's core collapsed under its own gravity, becoming an object of extraordinary density, a star composed almost entirely of neutrons, packed so tightly that the usual atomic structure dissolved and only the tiny, uncharged particles at the heart of atoms remained. They called this a neutron star. It was a bold idea. Neutrons had only just been discovered in 1932, a discovery made by James Chadwick, who found them at the Cavendish Laboratory in Cambridge. 2 years later, Baade and Zwicky were already imagining an entire star built from them. The object they were describing was almost beyond imagination, city-sized, unimaginably dense, the remnant of a catastrophic collapse. And they were right. But neutron stars were theoretical for a very long time. There was no way in 1934 to observe one. The idea sat in the literature, taken seriously by some physicists and more or less set aside by most for over 30 years. Fact 36. And then, in 1967, Jocelyn Bell Bernal was a graduate student at Cambridge, working with her supervisor, Anthony Hewish, on a radio telescope designed to study a completely different phenomenon, the twinkling of distant radio sources as the solar wind passed through them. She was analyzing chart recorder paper, looking for patterns in the static, and she found something that didn't fit, a small, regular, repeating signal, arriving every 1.3 seconds, precise enough that she and her colleagues couldn't immediately explain it. They called it scruff at first, a bit of messy signal, possibly interference from a television or a passing car, but it kept coming back. It arrived at the same sidereal time each day, meaning it was fixed to the stars, not to any source on Earth. It was unmistakably coming from somewhere in the sky, and it was repeating with a regularity that no known astronomical object could produce. The signal was briefly nicknamed LGM-1 for Little Green Men. It was a joke, mostly a way of acknowledging how strange the regularity was, how much it resembled something that might have been built rather than born. The team quickly moved past that idea, recognizing that if there were a civilization on the other end, it would be a very strange civilization whose only message was a metronomic pulse. But the nickname stuck in the popular telling, a reminder of the briefly disorienting strangeness of what they had found. Fact 37. What they had found was a pulsar, though the word itself came a little later. What they were seeing was a spinning neutron star, its beams sweeping across their telescope like a lighthouse beam sweeping across a shore. The regularity was real, and it was natural, and it was unlike anything in the catalogue. The Crab Pulsar was identified in 1968, not long after, and its identification was crucial for a reason that goes beyond simply adding a new object to the list. The Crab Pulsar sat at the center of the Crab Nebula. The Crab Nebula was already known to be the remnant of a supernova. And here, at the heart of that remnant, was a pulsing neutron star, exactly the kind of object that Barde and Zwicky had predicted in 1934 would be left behind by a supernova. The chain closed. The prediction matched the observation. Supernovae really did leave neutron stars, and neutron stars really did pulse. There was more. Thomas Gold, an astronomer at Cornell, proposed in 1968 that pulsars were rotating neutron stars, not oscillating, not orbiting, but spinning, and that what we saw as a pulse was the sweep of the beam with each rotation. It was a clean, simple model, and the Crab Pulsar provided the test. If Gold was right, if pulsars were spinning and slowing as they shed energy, then the Crab's pulse period should be measurably growing longer over time. And it was. The slowdown was real. The period was stretching by exactly the kind of amount a spinning, energy-losing object of that size and magnetic field strength should produce. Gold's model was confirmed. The Crab Pulsar was a spinning neutron star, and the energy it lost to space as it slowed was precisely what was lighting the nebula around it. The pieces fit together so cleanly that astronomers sometimes describe this confirmation as one of the most satisfying moments in the history of the field. Not a dramatic announcement, not a sudden flash of discovery, but a quiet convergence, a prediction from 1934, a theoretical model from 1968, and years of careful pulse timing, all pointing to the same answer. Fact 38. Now, let us spend a little time with the star itself, with its anatomy, with what it is on the inside and outside, and how it manages to be simultaneously one of the most extreme objects in the known universe and, from a certain angle, one of the most quietly remarkable. The Crab Pulsar's magnetic field is the first thing to reckon with. It is hard to express how strong it is in ordinary terms, but let us try. Earth has a magnetic field. You rely on it every time a compass needle swings toward north. That field is measured in units called Tesla. Earth's is roughly 50 millionths of a Tesla at the surface. A strong hospital MRI machine generates a field of a few Tesla. The Crab Pulsar's magnetic field is on the order of 100 billion Tesla, roughly 1 trillion times stronger than Earth's, 1 trillion. And it is this field, wound tight around a spinning star, that drives everything. The field rotates with the star 30 times a second. The rotating magnetic field accelerates particles to enormous energies and flings them outward. Those particles form the pulsar wind. The wind powers the nebula. The field also channels radiation into the two beams that sweep past Earth with each rotation. Everything about the Crab Pulsar's behavior, the pulses, the wind, the nebula's glow, traces back to that one fact: 1 trillion times Earth magnetic field, spinning without pause. Fact 39. Then there are the glitches. The pulsar's slow, steady spin down is not perfectly smooth. Occasionally, not often, not predictably, the Crab Pulsar briefly speeds up. The pulse period suddenly becomes a tiny fraction shorter. The star, for reasons that physicists are still working out, gives a small, sudden lurch and spins faster for a moment before settling back into its long decline. These events are called glitches. They are one of the more intriguing puzzles in pulsar physics, partly because the scale is so tiny, the change in period is a fraction of a millionth of the already small period, and partly because they offer one of the very few windows we have into the interior of the star. The most widely accepted explanation involves the pulsar's interior. Beneath the star's outer layers, matter under the extraordinary pressure of neutron star gravity behaves in ways that have no parallel in any material on Earth. One of the predicted properties is superfluidity, the ability of a fluid to flow without any friction at all. In ordinary life, all fluids have at least some viscosity, some resistance to flow: water, oil, air. They all slow down objects moving through them to some degree. A superfluid has no viscosity at all. It flows forever, never losing momentum. Physicists believe that a large portion of the Crab Pulsar's interior is a superfluid of neutrons, a region where the densely packed particles flow without friction, maintaining their own rotation independently of the star's outer layers. When the outer layers slow down, as they continuously do, losing energy to the wind, the superfluid interior can momentarily get ahead. The angular momentum of the superfluid can be transferred suddenly and catastrophically to the outer crust, giving the whole star a tiny kick forward. A glitch, in other words, is a neutron star momentarily tripping over its own insides, a small internal readjustment, and then the slow wind down continues as if nothing happened. Fact 40. The outer layer of the Crab Pulsar, the crust, the solid skin of this extraordinary object, is something else entirely. Neutron stars are predicted to have a crystalline outer crust, a lattice of atomic nuclei held in an ordered structure by forces we barely understand. This crust is thought to be far stronger than any material we have ever made or measured. Steel, the strongest ordinary structural material, can resist compression up to a certain point before it yields. The crust of a neutron star is thought to be roughly 10 billion times stronger than steel. 10 billion times! This is the kind of statement that is almost useless to try to visualize. Steel already feels strong to human hands. Multiply that by 10 billion and you have left the domain of any intuition we possess. The crust of the Crab Pulsar is simply something else, a state of matter that does not exist anywhere in our daily experience, that exists only because the gravity pressing down on it is itself unimaginable. And yet glitches suggest that even that crust sometimes shifts. Small rearrangements deep inside the star, tiny changes in the crystal structure as the star slowly settles into its long aging. A quiet starquake somewhere inside. Fact 41. The surface of the Crab Pulsar, if surface is even the right word for an object this strange, runs at a temperature of around 1 million degrees. 1 million degrees Kelvin, which is roughly the same as 1 million degrees Celsius for numbers this large. By comparison, the surface of our own Sun runs at about 5,500 degrees. The Crab Pulsar's surface is roughly 200 times hotter than the surface of the Sun. And yet it is cooling. Slowly, steadily, over the centuries, the Crab Pulsar is radiating heat and becoming slightly less hot. It is like an ember from a fire that burned nearly 1,000 years ago, still intensely, almost impossibly hot, but cooling, always cooling, on a time scale of millions of years. Long after it has lost enough rotational energy to stop lighting the nebula, it will still be cooling. The universe is patient, and so is the Crab Pulsar, and the two of them will be working through this slow transaction for a very long time. Fact 42. And now the clock. Because this is in some ways the most quietly remarkable thing about the Crab Pulsar, the thing that ties the whole story together and gives this particular dead star its special place not just in the catalogue of strange objects, but in the actual practice of astronomy as humans carry it out every night. The Crab Pulsar is a clock, not a metaphorical clock, not a clock in the way that any periodic natural process is loosely called a clock, but an actual practical working reference standard that astronomers have used for decades to calibrate their instruments and validate their measurements. Fact 43. The pulse arrives with extraordinary regularity. Once you account for the slow, predictable spin down, which is itself so regular it can be precisely modelled, the Crab Pulsar's timing can be predicted to a precision of many decimal places. The pulse will arrive, and it will arrive at the predicted time, and the difference between prediction and arrival will be immeasurably small. This is the behavior of a precision timekeeper. For years, when a new X-ray telescope was launched into orbit, one of the first things its operators did was point it at the Crab Pulsar. Not because the crab was necessarily the most scientifically interesting target at that moment, but because checking the telescope's timing and sensitivity against a known, stable, well-characterized source was the fastest way to verify that the instrument was working correctly. The crab was the reference. If your measurement of the crab matched what everyone else's measurement of the crab had always been, your telescope was calibrated. If it didn't, something was off, and the problem was yours, not the crab's. Fact 44. This role as a reference source gave rise to a unit of measurement that has become, in X-ray astronomy, an informal but very practical convention. The brightness of the Crab Nebula and pulsar system in X-rays is so consistent, so well known, and so broadly agreed upon that astronomers began using it as a benchmark. To describe a source as having a brightness of one crab is to say it shines in X-rays as brightly as the Crab Nebula and pulsar system combined. To describe a faint source as a millicrab is to say it shines at 1,000th of that brightness. The crab, the millicrab, a unit of brightness named for a cloud of gas 11 light-years across, powered by a city-sized dead star spinning 30 times a second in the constellation Taurus. It is perhaps the most unusual unit in all of astronomy, an entire object turned into a measuring stick so reliable that the field adopted it informally, and it simply stayed. Fact 45. And the precision of the Crab Pulsar's timing goes even further than calibration. It reaches into one of the most ambitious ongoing projects in modern astrophysics. You may have heard that gravitational waves were detected for the first time in 2015, ripples in the fabric of space-time itself, produced by pairs of massive objects spiraling together and merging. That detection was made by instruments called LIGO, laser interferometers that measured the stretching and squeezing of space directly. It was one of the great confirmations in the history of physics. But there is another way to search for gravitational waves, a longer, slower, more patient way. It uses pulsars. The idea is this: if a gravitational wave passes through the galaxy, it should stretch and compress the distances between us and the pulsars we are timing. The arrival time of a pulsar's pulse would shift, slightly early, then slightly late, in a pattern characteristic of a passing wave. To detect this, you need many pulsars spread across the sky, and you need to time them for years or decades with extraordinary precision. The network of pulsars acts as a kind of cosmic detector array, with each pulsar a test mass floating in the fabric of space. This technique is called pulsar timing arrays, and the Crab Pulsar, faithful and well characterized as it is part of the landscape of objects that inform this work. The steady, measurable, predictable ticking of pulsars like the crab is the very property that makes the technique possible. To find the faint signature of a gravitational wave in the timing data, you need to know the timing deeply, to model it precisely, to subtract out everything expected, and look for what remains. The Crab Pulsar's decades of careful timing records contribute to that understanding. In a sense, the Crab Pulsar is not just a clock, it is part of a galaxy-spanning instrument, a single tick in a web of ticks spread across thousands of light-years of space, all listening together for the quiet vibration of the universe's deepest architecture. Fact 46. It is worth pausing here as you settle into wherever you are tonight and simply holding that thought. This object, this city-sized remnant of a star that exploded while human beings were building cathedrals and trading along the Silk Road, while Song dynasty astronomers were making careful records of unusual lights in the sky, this object is, right now, serving as one of the instruments with which we listen for gravitational waves. The same pulsar that a court astronomer noted as a guest star in July of 1054, now a node in a listening array that spans the Milky Way. There is no precise word for that kind of continuity. It is not exactly awe, not exactly comfort. It is something quieter than either, the feeling of a very long thread running from a summer night in Song Dynasty China all the way to tonight, with the Crab Pulsar at the center of it, turning. Fact 47. Let us go back to the physics for a moment, because there is one more aspect of the Crab Pulsar's anatomy that deserves a quiet mention. Something with a name that is, for a theoretical concept in dense matter physics, surprisingly charming. Deep inside the crust of a neutron star, below the rigid crystalline outer layers, in the region where matter is under pressures that squeeze atomic nuclei into contact with each other, physicists have predicted that the material may arrange itself into unusual shapes. When nuclei are pressed together this tightly, the forces between them can cause them to assemble into elongated cylinders or flat sheets or strange, interconnected tubes, depending on the exact density and pressure at each depth. These structures have been given nicknames that acknowledge their resemblance to familiar foods. Physicists call them nuclear pasta, gnocchi-like spheres of nuclear material, spaghetti-like rods, lasagna-like sheets, buckled, tangled anti-spaghetti, sometimes called antipasta. Inside the crust of the Crab Pulsar, inside the crust of every neutron star, matter may be organized into these strange geometries, held in place by the overwhelming pressure of a star's worth of gravity pressing down from above. It is, of all the things in this long list of remarkable facts, possibly the most gently whimsical, that at the heart of one of the universe's most extreme objects, the matter is organized into something that a physicist reached for a pasta menu to name. The Crab Pulsar contains, somewhere in its crystalline layers, a zone that physicists call nuclear pasta, and they mean it literally. And it is one of the strangest sentences in astrophysics. Fact 48. The magnetic field we spoke of, that trillion times Earth field, is also the source of something that took astronomers longer to nail down than almost anything else about the crab: the beams. The pulsar emits two beams of radiation. They emerge roughly from the magnetic poles of the star, the points where the field lines converge most strongly, and they shoot outward into space like the beams from a lighthouse. But here is the crucial detail. The magnetic poles are not aligned with the rotation axis of the star. The axis around which the Crab Pulsar spins is tilted relative to the axis of its magnetic field. So as the star spins, the beams don't point steadily in two fixed directions. They sweep around in wide circles like a lighthouse beam swinging around its full arc. And once every 33 milliseconds, one of those beams sweeps past Earth. We see a flash, a pulse, 30 times a second. This geometry is the reason we see it pulse at all. If the pulsar's magnetic axis were aligned with its spin axis, the beams would simply point in the same directions forever, and we'd see a steady glow, not a flash. It is only because the axes are tilted, only because the star's magnetic personality and its rotational personality are slightly out of sync, that the beam sweeps the sky and we catch it on each pass. And this means something else. There are neutron stars whose beams never sweep past Earth at all, stars spinning just as faithfully, pulsing just as steadily, that we simply cannot see because the geometry of their spin and magnetic field never points a beam in our direction. The crab is visible to us not because it is special in its behavior, but because it is lucky in its geometry. Its beam happens to cross our path on each turn. Fact 49. The Crab Pulsar's timing, the precise measurement of those 30 pulses per second, is also a kind of window into the constancy of physics itself. Because the pulsar emits pulses across so many different wavelengths, radio waves, visible light, X-rays, gamma rays. Astronomers can time the arrival of pulses at all these different energies and compare them. According to our best understanding of physics, light of all wavelengths travels at the same speed in a vacuum. If that is true, a pulse emitted simultaneously in radio and in optical light should arrive at our telescopes at the same time, despite having traveled for 6,500 years. And it does. The pulses in different bands of light arrive in step with each other, exactly as predicted. This is not a trivial confirmation. It is a test of one of the deepest assumptions in physics, carried out over a baseline of 6,500 light-years, and the Crab Pulsar passes it every time. Fact 50. There is one more layer to the Crab Pulsar's role as a faithful, patient instrument of the universe, and it has to do with the journey the pulse makes between the star and us. Space is not empty. Between the Crab Pulsar and Earth, there is gas. Diffuse, thin, spread very thinly through the 6,500 light-years of the galaxy's disk, but there. And radio waves of different frequencies travel through this gas at slightly different speeds. Lower frequency radio waves are slowed a little more than higher frequency ones, arriving at our telescopes a fraction of a second later. This effect is called dispersion, and the amount of dispersion in a pulsar signal tells you how much material lies along the line of sight between the pulsar and the telescope. The Crab Pulsar's pulse has been dispersed. The radio signal that reaches us carries, encoded in the slightly staggered arrival of different frequencies, a measurement of the gas between us and the crab. Astronomers use this number, the dispersion measure, to map the distribution of gas in that part of the galaxy. The pulsar, simply by being there and pulsing, doubles as a probe of the interstellar medium it shines through. It illuminates not only the nebula immediately around it, but the vast column of space between it and us. Everything it tells us about that space is simply there, encoded in the pulse, waiting for instruments patient enough to read it. Fact 51. And so here we are, halfway through our 100 facts, somewhere in the quiet depth of this long and gentle walk through one of astronomy's most reliably interesting objects. You might be drowsy by now. If you are, that is exactly right. There is no urgency here. The Crab Pulsar will keep turning for millions of years. These facts will all still be here in the morning if you want them. And even if you drift off before the end, you have already learned something true about a dead star that has been keeping its patient vigil since before the Norman conquest. The slowdown, the pulsar wind, the synchrotron glow and the hydrogen filaments, the prediction from 1934 and the confirmation from 1968, the crystalline crust, stronger than any steel, the superfluid interior and the glitches, the million-degree surface cooling slowly over centuries, the magnetic field 1 trillion times our own, the calibration source, the crab and the millicrab, the unit named for a nebula, the pulsar timing arrays, listening for the vibration of space-time itself. All of this from one small, dense, turning star in Taurus. Fact 52. Let us rest on one of the stranger implications of the spin down before we move on. If the Crab Pulsar is slowing down now, losing 38 nanoseconds of period each day, then it must have been spinning faster in the past. Work backward through the physics, and the numbers suggest that at the moment of its birth, the Crab Pulsar may have been spinning many hundreds of times per second, perhaps as many as several hundred rotations in each single second.
Imagine that, the same star that turns 30 times a second tonight, which is already faster than you can follow. Imagine it spinning 10 times faster than that, or more. In the first moments after the core collapse, in the chaos of the supernova explosion, a stellar remnant the size of a city spinning hundreds of times each second, its magnetic field wound so tight the energy output is almost incomprehensible.
And then the slow exhale begins. The wind goes out. The energy flows away. The nebula inflates. The The period grows day by day, nanosecond by nanosecond. Over the 970 or so years since 1054, the Crab has already slowed from that frantic birth, spin down to the 30 rotations per second we measure today, and it will keep slowing for millions of years more, until eventually it is turning only once every several seconds, and then every several tens of seconds, and the beam is too weak to reliably detect, and the nebula has long since cooled and dispersed, and what remains is a quiet, dim neutron star, still there, but silent. Fact 53. There is something almost restful in that trajectory. The Crab Pulsar, in its long life, is doing what all energetic things do, gradually, inevitably coming to rest. It began frantic and became steady, and it is becoming steadier still, and one day, many millions of years from tonight, in a universe that will look very different from the one we inhabit, it will simply be a cold, dark ball of matter, dense beyond imagination, drifting quietly through the galaxy. But not yet, not for an extraordinarily long time. Tonight it is 30 times a second, and the nebula is glowing, and the pulse is arriving at our telescopes right on schedule. Fact 54. One more thought about what the spin down tells us: the age. We know the Crab Pulsar was born in 1054 because humans wrote it down. But in the absence of that historical record, physicists could still estimate its age from the spin down alone. The ratio of the current spin period to the rate at which that period is growing gives an estimate of how long the star has been slowing. This quantity is called the characteristic age. For the Crab Pulsar, the characteristic age works out to roughly 1200 years, not a perfect match to the actual 970 years since 1054, because the spin-down rate hasn't been perfectly constant, but close enough that it was one of the things that helped astronomers confidently link the pulsar to the historical record. The pulsar, in other words, can tell you roughly how old it is, simply from the rhythm of its own slowing. It carries its age in its pulse, like a tree carries its age in its rings. Fact 55. And the Crab Pulsar is young. Remarkably, unusually young, as pulsars go. Most of the pulsars we know about are thousands or millions of years old. They have already done most of their slowing. Their periods are measured in seconds, not milliseconds. Their nebulae, if they ever had them, have long since dispersed. They are quieter, dimmer, less energetic than the Crab. The Crab Pulsar is under 1,000 years old in pulsar terms. That is, an infant. It is still spinning fast, still pouring enormous energy into its surroundings, still driving the brightest and most clearly structured pulsar wind nebula we know. Its relative youth is one of the reasons it has been studied so intensively. It is telling us what pulsars look like when they are new, when their energy is high, and their impact on the surrounding space is at its most dramatic. And we know its birthday. That is the rarest of gifts in astrophysics, where ages are usually inferred and uncertain. The Crab Pulsar was born in 1054. We have a date carved into the records of the Song dynasty and corroborated by other witnesses from other lands. The pulsar and the historical record are joined at that single point in time, and that joining makes both the astrophysics and the history richer for it. Fact 56. The faithful clock, the calibration source, the reference that anchors the measurements of telescope after telescope, decade after decade. Let us linger here for just another moment, because there is something in this aspect of the Crab Pulsar that connects, in a quiet way, to why this particular list exists. We built this list around the idea of the Crab Pulsar as a timekeeper, not because that is the only thing it is. It is clearly many things, dramatic and strange and beautiful, but because the timekeeper framing is the one that pop science coverage tends to skip. The usual story focuses on the extreme, the density, the spin, the magnetic field, the power. All of those things are real and astonishing. But the reliability, the clock-like steadiness, the patience, the fact that it has been turning at this measured, knowable rate since before the Normans landed in England, that is the thread this list has been following. And the reason it matters for a list meant to ease you towards sleep is this: reliability is soothing, extremity is exciting. And the Crab Pulsar manages to be both at the same time. It is one of the most extreme objects in the known universe, and it is also one of the most dependable. It is what you get when you take the most violent event in stellar evolution and wait 1,000 years for it to settle into its rhythm. The violence is ancient history. What remains is a steady pulse, arriving right on time, 30 times a second every night, including tonight. Including right now, the beam is sweeping, the pulse is traveling. Somewhere a telescope is recording it, adding today's measurement to a dataset that stretches back decades, and you, wherever you are resting while it turns. There is more to come. The fine texture of the pulse itself, the giant bursts and the gamma-ray surprises, the ways the crab has been used to study objects in our own solar system, the Nobel Prize and its complicated footnote, the sonified ticking that sounds when you listen to it like a heartbeat. But we have time. The pulsar is not going anywhere, and neither for now are you. Let the spin down continue its patient work. Let the nebula keep its gentle glow. Let the number 38 nanoseconds settle somewhere in your mind, small and exact and oddly comforting. The daily, measurable signature of a star spending itself steadily in light. Let us think about the pulse itself for a moment. Not the fact of it. We have already spent time there, the 30 rotations a second, the 33 milliseconds, the beams sweeping past like a lighthouse in the dark. But the shape of it, because if you were to look at a single pulse from the Crab Pulsar, written out as a graph, a little wave traced across a page, you would notice something unexpected. It is not a simple spike. It is not one clean peak and then silence. There are two of them. Astronomers call them the main pulse and the interpulse, and together they arrive like a heartbeat, a stronger beat, then a softer one, then the pause, then the stronger beat again, lub-dub, lub-dub, 30 times a second, in radio waves and in visible light and in X-rays, the same double signature repeating with almost no variation. The two pulses come from the two beams, sweeping past us at slightly different moments in each rotation. One beam grazes us more directly, the other passes at a slightly different angle. The result is that the crab's pulse, if you could slow it down and listen to it, would sound less like a click and more like a gentle double knock. A soft knock on a door 30 times a second from 6,500 light-years away. There is something almost companionable about that image. A double knock, as if the star is checking in.
And mostly the pulse is exactly that reliable. 30 times a second, the same shape, the same timing, year after year. But occasionally, and this is one of the small, delightful surprises the crab keeps tucked away, it does something unexpected. It shouts.
These are called giant pulses, and the name is apt, though the word giant requires a little context. In terms of how long they last, giant pulses are anything but large. They are extraordinarily brief, lasting only millionths of a second, sometimes even less. A microsecond, a few microseconds. In human terms, this is a duration so short it is essentially undetectable without instruments. The blink of a camera shutter is about 10,000 times longer. And yet in that sliver of time, the Crab Pulsar briefly blazes in radio waves, enormously. These giant pulses are among the brightest, briefest radio flashes that any steady source in the sky is known to produce. In the moment of a giant pulse, the crab outshines everything around it at those wavelengths, then subsides just as quickly, folding back into its patient, regular rhythm as if nothing had happened. What causes them is not entirely clear. They fit within the normal pulse timing. They occur at the same rotational phase, at the same moment in each turn of the star. But their brightness is orders of magnitude above the average. Something in the pulsar's magnetosphere, that strange region of plasma and tangled magnetic field lines surrounding the star, occasionally conspires to produce a burst of coherent radio emission so bright it briefly overwhelms everything else. Then it passes. The steady double knock resumes. You can think of it like a very old clock that keeps perfect time, except that every so often, unexpectedly, it chimes loudly once before returning to its quiet tick. The chime is brief, the tick goes on, and somehow the tick is more reassuring for the contrast. There are no giant pulses right now as far as anyone knows. Or perhaps there are. They happen without warning, and the radio telescopes that monitor the crab are not always pointed its way at the exact right moment. That is another of the crab's gentle qualities. It does not need an audience. Whether or not anyone is listening, the pulse goes on. But the crab's capacity for surprise does not end with giant pulses. There is a larger kind of surprise, less brief, but no less interesting. In 2010 and then again in 2011, astronomers using two space-based gamma-ray observatories noticed something they had not seen before. The Crab Nebula, not just the pulsar, but the broader nebula itself, produced brief flares of very high-energy gamma rays. These were detected by two instruments, one called Fermi, which was designed specifically to survey the gamma-ray sky, and another called Agile, an Italian space telescope with a similar purpose. The flares were surprising because the Crab Nebula, after decades of observation, had come to be treated almost as a calibration standard, a steady source, a reliable benchmark. To say something had a brightness of one crab in X-rays was to compare it against this one dependable object. And yet here, in the gamma-ray regime, the nebula briefly and unexpectedly brightened in ways that did not seem to originate from the pulsar itself, but from the surrounding nebula, from the energetic particles moving through it. Astronomers were not alarmed exactly, but they were surprised. Even this well-studied object, this near-constant companion of generations of observers, could still produce something new. The gamma-ray flares lasted a few days. Then the crab settled back to its familiar glow. The episode was added to the long, careful record of observations, and theorists set to work on explanations involving rapid particle acceleration in the nebula's magnetic field. No firm consensus has settled, but that is one of the qualities of honest science. It adds things to the list of what needs explaining, and it keeps the list open. There is something restful in that, actually. An object this well-studied still has questions. The record is rich and the facts are many, but the understanding is never quite complete. The universe is generous with its mysteries and patient about resolving them. Now let us move from the pulse outward, from the star's beating heart to the structures it drives in the space around it, because the Crab Pulsar does not simply emit pulses and sit quietly. It inflates a whole architecture around itself, and some of that architecture is extraordinarily beautiful. Closest to the pulsar, within the X-ray images taken by the Chandra X-ray Observatory, astronomers have photographed something that looks, at first glance, almost like a fountain. There are rings, faint, expanding rings moving outward from the star, and a jet of emission stretching along the pulsar's spin axis. The jet punches outward in two directions, a thin line of glowing material driven by the pulsar's energy. And surrounding it all, there are what astronomers call wisps. Wisps are exactly what the word suggests. Delicate, shifting structures, brighter patches in the nebula near the pulsar that drift and change on timescales of weeks to months. Time-lapse sequences assembled from Hubble's Space Telescope images show them moving outward like ripples, spreading from a dropped pebble in still water. They appear, they drift, they fade, and new ones form behind them. The process is continuous, driven by the pulsar wind, the stream of particles that flows outward from the spinning star and presses against the surrounding nebula like a wind pressing against a curtain. If you have ever sat near a fire and watched the smoke rise and shift, wisping upward in slow, curling patterns, you have a loose intuition for what the Crab's inner nebula looks like in time-lapse. It is not quite that gentle. The speeds involved are not gentle at all, but the visual quality is something like that. A slow drift, a shimmer, a fountain of light surrounding a turning engine too small to see directly. The whole system, the jet, the rings, the wisps, the pulsar wind pressing outward, has become one of the defining images of what astrophysicists call a pulsar wind nebula. It is the structure that forms when a pulsar's wind runs into its surrounding shell of supernova material. The Crab was the first such structure recognized for what it was, and it remains the most studied example. When theorists build models of how pulsar wind nebulae work, they almost always start by asking whether the model can reproduce the Crab, and so the Crab is not just an object, it is a template, a teaching example written in light. We should pause here for just a moment. If you are still awake, and perhaps you are, that is fine, there is no obligation. Let us allow the image to settle. A 20-kilometer star, impossibly dense, spinning 30 times a second, blowing a wind of charged particles outward in all directions. That wind presses against a shell of gas that was once the outer layers of a star many times larger than the Sun. The pressure inflates the shell from within, lighting it up, sending wisps drifting outward, maintaining the blue-white inner glow and the red hydrogen threads beyond. And at the center of all of it, too small to see, the pulse continues. Main pulse, interpulse, main pulse, interpulse, a system in balance, or rather, in very slow imbalance, tilting incrementally towards silence over millions of years. But tonight, in balance enough. Now the Crab has done something else remarkable, something that connects this faraway dead star to objects much closer to home. It has served more than once as a tool for studying things within our own solar system. Here is one example. Saturn's largest moon is Titan. Titan is a world with a thick atmosphere, thick enough that it was hard, from early observations, to measure exactly how that atmosphere was structured at different altitudes. One way to probe it is to watch what happens when a distant bright source passes behind Titan as seen from Earth. The source's radiation has to travel through the edges of Titan's atmosphere to reach us, and the way it is absorbed or delayed tells you something about what the atmosphere contains at each height. For this technique to work, you need the background source to be very bright, very compact, and very steady, a precise point of light whose normal behavior is completely understood. The Crab Nebula, particularly bright in X-rays, happens to be a near-perfect candidate, and indeed it has been used in exactly this way, its X-ray light filtered through the outer layers of Titan's atmosphere as the geometry aligned, yielding information about that distant moon from a source of radiation 6,500 light-years beyond it. A dead star patiently providing a backlight for the study of a moon in our own neighborhood. And there is another example, closer in time. Long before Hubble and Chandra were in orbit, astronomers had a simpler instrument available to them, the moon. Our own moon, drifting across the sky each month, occasionally passes in front of the Crab Nebula from Earth's perspective. These events are called lunar occultations. And for early radio astronomers especially, watching the Crab gradually disappear behind the moon's limb and then reappear was extraordinarily useful. The timing of the disappearance and reappearance, measured carefully, could be used to pin down the exact position of the Crab and to probe the structure of its radio emission. At those wavelengths, the nebula is not a perfect point. It has extent, and the way different parts of it disappeared as the Moon advanced across it told astronomers something about its shape and inner structure. Our own Moon, in other words, helped measure the Crab, a local body used as a precision tool to study something vastly farther away. The universe has a way of making neighbors useful. Let us turn now to something that touches on the age of this object and what its future might look like. A thread of time that runs from its birth right through to tonight and stretches forward, very far forward, into a quiet ending. The Crab Pulsar is young, not young in human terms, of course, is nearly 1,000 years old, measured from the night of its explosion, but in pulsar terms, 1,000 years is barely anything. Most pulsars we know of are millions or tens of millions of years old. The Crab is a newborn by comparison, and this matters enormously for what we can learn from it, because almost no other pulsars in the sky have a known, precisely dated birth. The Crab's birth year is 1054, or rather the light of its birth reached Earth in 1054, making the actual explosion around 5400 BC. Either way, the date is known, anchored in the historical record, confirmed by the expansion of the nebula traced backward in time. So when astronomers look at the Crab and measure its current spin rate, its current spin down, its current magnetic field, and its nebula's brightness, they are looking at a pulsar whose age they know exactly. They know how old it is. This makes it something close to irreplaceable as a calibration point for theories of how pulsars evolve. What do those theories say about the Crab's future? The spin down is real and it is steady. 38 nanoseconds per day, the period lengthens. That rate will itself change very slowly over time. Pulsars do not spin down at a perfectly constant rate, but the general trend is clear. The star is spending its rotational energy slowly, sending it outward as wind and light. As the spin slows, the pulsar's output decreases. The nebula, which depends on that energy to stay bright, will in time begin to dim. Not on any time scale a human civilization need concern itself with, but on the deep time scale of the universe, yes. The Crab Nebula will eventually fade. The wisps will still. The synchrotron glow will cool. The red filaments, no longer energized by the pulsar's wind, will disperse into the general gas of the galaxy, and the pulsar itself will spin down over millions of years, not thousands, millions, until eventually it becomes what is called a dead pulsar, or a cold neutron star. A sphere of neutron matter 20 kilometers across, dark, immensely dense, drifting through space, still there, still solid, just no longer turning fast enough to produce the beams, no longer connected to us by a pulse. The clock will not stop. It will merely become too slow to notice. But that is an almost incomprehensibly long time away. On any human timescale, and on any timescale relevant to us tonight, the Crab is turning. The beam is sweeping. The pulse is traveling. There is one more piece of human history woven into this story, and it is worth sitting with because it is not entirely comfortable. It is the story of the Nobel Prize. In 1974, the Nobel Prize in Physics was awarded in part for the discovery of pulsars. The prize went to Anthony Hewish, the radio astronomer who ran the research project at Cambridge and who designed and built the radio telescope array that made the detection possible. He received a share of the prize specifically for his role in the discovery. But the person who actually found the signal, who sat with the chart recorder paper, who noticed the faint, regular bit of scruff in the data, who kept careful records and drew it to Hewish's attention, who did the painstaking work of ruling out interference and confirming the signal's extraterrestrial origin, was Jocelyn Bell Burnell. She was a graduate student at the time. She was not awarded the Nobel Prize, This omission was noted at the time and has been discussed ever since. Belle Burnell herself has spoken about it over the years with a remarkable grace, neither dismissing the disappointment nor allowing it to define her long and distinguished career. She went on to become one of the most respected astrophysicists of her generation, eventually receiving numerous honors, and in 2018 she was awarded the Special Breakthrough Prize in Fundamental Physics, which she donated in its entirety to fund scholarships for students from underrepresented groups in physics. She turned a complicated piece of history into something generative. The Nobel Committee does not explain its decisions, and so the reasoning behind Belle Burnell's exclusion can only be inferred. But the episode has become one of the quiet, recurring conversations in the history of science, about how credit is assigned, about whose work is visible and whose is not, about the structures that shape what gets recognized. It does not diminish the discovery, it does not diminish the object. The Crab Pulsar turns regardless. But the human story attached to it is not entirely tidy, and a careful list should say so. It is a gentle historical footnote noted here without drama. The star does not carry the weight of human politics, it only carries its own patient turning. And now let us come to something that brings all of this very close, something that makes the Crab Pulsar less abstract, if only for a moment. The pulse has been recorded and converted into sound. This is a process called sonification, taking data that exists in a form humans cannot directly perceive and mapping it into a form they can. Radio pulses become sound waves, brightness variations become tones, timing becomes rhythm. And when researchers have done this with the Crab Pulsar's signal, slowing the data enough to fall within the range of human hearing, the result is something unexpectedly familiar. It sounds like a heartbeat, or like a metronome set to a slow, steady beat. A soft, regular thump, repeating with almost mechanical precision. People who hear it for the first time often describe the same reaction, surprise and then a kind of calm. There is something in regular rhythm that the nervous system responds to. Something that signals safety, steadiness, the absence of alarm. A heartbeat is one of the earliest sounds a human being is aware of, heard from before birth. And here is a dead star, 6,500 light-years away, producing a signal that when translated into sound, gives the same impression of patient, reliable beating. It is not, of course, a heartbeat in any biological sense. The star has no heart, no blood, no warmth of life. But the signal it produces carries something of the same quality, the quality of regularity, of something that continues without effort, without intention, simply because the physics of its situation produces it. A spinning star producing a sweeping beam is not trying to send a signal any more than a lighthouse is trying to communicate with ships. The lighthouse turns because a motor turns it. The pulsar turns because the collapse of a massive star set it spinning and conservation of momentum kept it going. The meaning we find in the rhythm is ours, not the star's, and yet the rhythm is real, the pulse is real, the steadiness is real. If you were to listen to a recording of the Crab Pulsar's sonified signal tonight, and recordings of it exist, made by radio telescopes and converted into audio by researchers at various institutions, you might find it an unusually literal kind of lullaby, a ticking from deep space, a clock that has been running for nearly 1,000 years, since before any clock made by human hands still survives. Ticking while the Song dynasty kept its records, while Lord Rosse sketched it through his enormous telescope in Ireland, while Jocelyn Bell Burnell worked through her reels of chart recorder paper, while the first Chandra images revealed the wisps and the jet. Ticking tonight while you rest. That is worth holding for a moment. The Crab Pulsar has been ticking without interruption since before the Norman conquest. Every second of every day since July 1054, when the guest star appeared over China and the astronomers wrote their careful records in the palace records, Every second since then, the beam has been sweeping, the pulse has been traveling 30 times a second, adding up to millions per day, billions per year, an unbroken sequence of pulses traveling outward through the galaxy, arriving at telescopes and at the thin upper atmosphere of this planet, and now folded into a conversation that is putting you gently to sleep. There is a particular kind of comfort in unbroken things, not flashy, not dramatic, just the quiet confidence of a thread that has not broken. The Crab Pulsar's pulse is that thread. Through every century since 1054, through the rise and fall of empires and languages and entire civilizations, through every invention and discovery and tragedy and wonder that has occurred on this small planet, that beam has been sweeping and the pulse has been arriving, regular and patient, from 6,500 light-years out. It does not know about any of that. It is a dead star, but we know. And knowing it has that quality, that unbroken constancy stretching back through 1,000 years of human history, changes the texture of the fact. It becomes less a piece of physics and more a kind of anchor. Something that has been here, that has been arriving quietly, consistently, for longer than any human institution, any city, any written tradition we can still read. That is not a small thing. And now we have come nearly to the end of our list. Not quite. Let us gather a few last things before we turn off the light. Small things, soft things. The kind of details that are pleasant to carry into sleep. The constellation Taurus, where the Crab Nebula sits, rises in the autumn in the northern hemisphere and crosses the sky through the long winter nights. For many months of the year, if you are in the right part of the world and the sky is dark enough and you know where to look, you can find it, a faint smudge near the tip of one of the bull's horns. You will not see the pulsar, of course. That is far too faint. You will barely see the nebula itself without a telescope. Under city skies, you will likely not see it at all. It is one of those objects that rewards patience and darkness and stillness, the kind of object you have to earn. And that, too, is a fitting quality for a sleep list. The Crab Nebula is a reward for stillness, for dark skies and quiet eyes, and the willingness to stand outside long enough for your eyes to adjust. It is not flashy. It does not demand attention. It is a faint, soft smudge with a secret, an extraordinary, violent, ancient secret tucked inside. The word nebula, by the way, simply means cloud in Latin. A cloud. It is one of the more understated names in the astronomical catalogue, a cloud in Taurus. And inside the cloud, a dead star the size of a city, spinning 30 times a second. Charles Messier, the French comet hunter, who catalogued the nebula as the first entry in his famous list in 1758, was not interested in nebulae for their own sake. He was annoyed by them. He listed the Crab and the 100 or so other nebulae and clusters that followed it, so that other comet hunters would not mistake these fuzzy, stationary objects for the fuzzy, moving objects that were his real quarry. M1, first on the list, earned its number by being a beautiful distraction, a nuisance to one astronomer, a treasure to every astronomer who came after. That too has a gentle quality to it. The most studied supernova remnant in the sky, the textbook example of a pulsar-wind nebula, the anchor of a unit of astronomical brightness, the object against which radio telescopes have been calibrated and theories of neutron stars tested. All of it started as an entry on a list of things to ignore. And underneath all the science, underneath the spin-down timing and the pulsar wind nebula models and the dispersion measures and the gamma-ray flares, the Crab Pulsar is simply this: a tiny, enormously dense, rapidly spinning core left behind when a giant star could no longer hold itself up. The core collapsed. The outer layers exploded outward. The collapse happened in less than a second. A star many times larger than the Sun became something 20 kilometers across in the time it takes to say one word, and then it began to spin, and the spinning produced a field, and the field produced beams, and the beams swept across the galaxy, and one of those sweeps and one of those lighthouse flashes reaches us regularly still. The outer layers that were flung outward in the explosion are still out there, still expanding. The lacy red threads you see in photographs of the crab are those layers. The former outer skin of the star, lit up by the pulsar's energy, glowing in hydrogen emission. They form a kind of cage around the bluer inner glow, and inside the cage, the pulsar wind presses outward, keeping the whole structure inflated, maintaining the glow against the slow pull of expansion and cooling. Without the pulsar, the nebula would fade. Without the energy coming from that spinning city-sized core, the crab would dim and the filaments would disperse, and in time, the whole thing would blend invisibly into the general interstellar medium. The pulsar is, in a gentle sense, the nebula's caretaker. It keeps the light on. It has been keeping the light on for nearly 1,000 years. And in that light, woven into the filaments and the wisps and the synchrotron glow, are elements: carbon, oxygen, calcium, iron, forged in the original star over millions of years of nuclear burning and scattered into space by the explosion. Some of those atoms will one day, not soon, but one day, on the vast timescale of stellar evolution, become part of new molecular clouds. New clouds will collapse. New stars will form. Perhaps new planets will circle them, and on those planets perhaps material that was once part of the star that became the Crab Pulsar will be part of something else entirely. A rock, a sea, something more complicated. This is the kind of thought that can feel vertiginous if you hold it too tightly, so let it be light. Let it be a gentle, passing wonder rather than a difficult one. The universe recycles. The crab is part of that. Its elements are already in transit, already beginning the long journey back towards something new. But the pulsar itself, that stubborn, dense, spinning core, is on a different timeline. It will be there for millions of years yet, slowing by 38 nanoseconds a day, spending its spin in light, keeping its patient, double-beat rhythm until the energy is too low to sustain the beams and the lighthouse goes dark. Not tonight. Not for a very, very long time. Tonight, it is still spinning. And now, we are here. At the end of the list, and at the end of the night, we have come a long way from the opening, from the first fact, that extraordinary image of a city-sized star only 20 kilometers across, spinning 30 times a second, to this quiet close. Along the way, we spent time with the Song dynasty astronomers who looked up in July 1054 and wrote down what they saw: a xing, a guest star, sudden and bright, visible in the daytime for weeks. We spent time with Fujiwara no Sadai's record of a Japanese observation, and with Ibn Butlan's Arabic account, and with the quiet puzzle of why Europe said so little about a light that should have been impossible to miss. We sat with Charles Messier and his Comet Hunters catalogue, with Lord Ross and his enormous telescope in Ireland, sketching something that looked vaguely like a crab. We traced the nebula's 11 light-year span, its filaments still moving outward at 1,500 kilometers a second, its soft glow sustained from within by a spinning dead star. We found Jocelyn Bell Bernal sitting with her chart recorder paper in 1967, noticing something regular in the noise. We found the pulse with its double beat, the giant bursts that last only millionths of a second, the wisps drifting outward in Chandra's X-ray images, the gamma-ray flares of 2010 and 2011 that surprised even the most experienced observers. We found the crab used as a backlight for Titan's atmosphere, and as a reference lamp against which telescopes were calibrated, and as a standard candle so reliable that astronomers invented a unit named after it. 1 crab, 1 millicrab. We found the Nobel Prize that came with a complicated footnote. And we found the sonified pulse, that soft, rhythmic ticking that sounds when you slow it down into human hearing range, like a heartbeat, or a metronome, or a very old, very steady clock. Here is what I want you to carry into sleep, if you carry anything. That pulse is still happening, right now, wherever you are, in a bed, under a blanket, with a lamp still on or a phone screen dimming. The Crab Pulsar is spinning about 30 times a second, as it has been every second since 1054. It is slowing very slightly by 38 nanoseconds today. It is about 6,500 light-years away, which means the pulse currently arriving at Earth's atmosphere left the star long before you were born, long before anyone now alive was born, traveling quietly through the dark between the stars. It does not know you exist. It does not know anything. It is a 20-kilometer sphere of neutron matter, cooling slowly, spinning steadily, embedded in a glowing cloud of its own past. But it has been turning all your life and all your parents' lives and all the lives of every person who has ever looked up at the sky and felt the particular feeling of smallness and wonder that the sky produces. The Crab Pulsar was turning when the first radio telescopes were built, when Charles Messier was alive and chasing comets, when the first printed books appeared in Europe, when the Song dynasty court astronomers wrote xing in their records and looked up at a sky that had changed. That unbroken thread stretches from July 1054 to tonight, one continuous turning, one lighthouse that has not gone dark. Back at the very beginning of this list, you were somewhere, wherever you are right now. Maybe you have not moved since we started. Maybe you have shifted, grown warmer, let go of the day's particular weights. Maybe you drifted and came back, which is fine. The facts were here the whole time. I want to ask you the question I always ask, because I'm always genuinely curious about it. Where are you listening from tonight? And what time is it in your corner of the world? It could be the deep quiet of 3 in the morning, or the early dark of a winter evening, or a lazy weekend afternoon that turned somehow into a nap. Wherever it is, whatever time it is, the Crab Pulsar is spinning from the same spot in Taurus, 6,500 light-years out, the same as always. If you would like to leave that in the comments, where you are, what time it is, I would love to know. This channel is a small, quiet place, and knowing that you are out there in your particular corner of the night means something. And if you have found your way here for the first time tonight, and something about this slow, patient list felt like the right company for going to sleep, a like and a subscribe genuinely helps this sleepy little channel keep making things like this. Small creators like me rely on that kind of support to keep the lights on, or in this case, to keep making content designed specifically to help turn the lights off. It does not cost you anything, and it means more than you might expect. To those of you who have been here before, who come back night after night for this kind of slow journey through one strange and wonderful thing, thank you. Thank you for being part of what this channel is. The Crab Pulsar is still spinning, 30 times a second, a little slower than yesterday by a nearly undetectable amount, its double beat moving steadily through the dark. The nebula around it glows its soft blue-white glow, the red filaments framing it like a net of old light. Somewhere, a telescope is recording tonight's pulse timing, adding a data point to a record that stretches back decades, one more small contribution to the long, careful project of understanding what this extraordinary object is. And you are resting. Wherever you are, whatever the hour, that is enough. That is, in fact, everything. Calm mind, clever dreams. I'll be here tomorrow night.